In today's lecture, we're going to be talking about the union of polyhedra. So our setting is where we have k different polyhedra, and each one is denoted by pi for I that goes from 1 to k. And polyhedron pi is in the space Rn and is defined by the system AIX less than or equal to bi. So we already considered the setting where we have k polyhedra and we're interested in the union. And what we did in chapter 2 is that we actually derived an extended formulation for the convex hull of the union of all these polyhedra. But there we made a very important assumption, which was that each pi is a polytope, so it's a bounded polyhedron. What we're going to do in this section instead is relax this assumption and consider the general case. So there's already immediately a problem that didn't appear in the bounded setting. In fact, here, in the general case, it can happen that the convex hull of all our polyhedron may not be closed. So in particular, of course, since every polyhedron is a closed set, this convex hull may not be a polyhedron at all. And you can easily construct an example where this happens already in dimension 2. Everything you need to do is to pick a line, L, and a point which is not contained on the line. And now if you construct the convex hull of these two sets, you will immediately see that this is not closed. So in particular, not a polyhedron. So, well, we can't then think about constructing an extended formulation for this set in general using only linear inequalities because, of course, this is not polyhedral. However, we're going to do the next best thing in a sense. So we're going to instead characterize the closure of such a set. So the topological closure of the convex hull of the union of the PIs. And this is always how we're going to denote the closed convex hull. We have here an example, just to understand what we're talking about. We have a polytope here P1 and a polyhedron P2. And the set over here on the right is exactly the closed convex hull of the union of the two. Note that for this very specific example, the set that you would obtain without the closure, so this, just the convex hull of the union, would not contain this line. This line here is only present in the closure of the convex hull. Good. So this is our main result. It's the Ballast's theorem on the union of polyhedra. And we are not going to prove these results. And in fact, the reason is that this both the statement and the proof are very similar to the bounded case that we saw in chapter 2. But here, in order to derive the result, we need one more assumption. Plus, of course, we need to consider the closed convex hull instead of the convex hull. So these are the main two differences. So let Y be the polyhedron described by this system. So what we're doing here is the following. First, what variables do we have? We have the original x variables, these are the Rn variables. Then for every polyhedron pi, we have a copy of the x variables that is denoted here by xi. And finally, we have one more variable for every polyhedron, which is the delta I. Good, so at this point we do exactly what we did in chapter 2. So we write x as the sum of all the xi's, and then we take the system defining the polyhedron I and multiply the right hand by delta I. That's exactly what we have, and also we need to replace the variable x with the copy of the variables x corresponding to the ith polyhedron, so xi. So that's what these inequalities are. Then we have that the sum of the delta I is equal to 1 and delta I are all greater than or equal to 0. So this system is exactly the same as the one we looked at in chapter 2. Now the theorem says that if all the polyhedra pi are non-empty, then the closed convex hull of the union is the projection of y onto the X space. So the differences are that first, we need to assume that all the polyhedra are non-empty, which is a condition that we didn't have in the polytope case. And secondly, the extended formulation is for the closed convex hull of the union and not for the convex hull as we did in chapter 2. We will not prove this result, and the proof is, of course, an extension of the one we saw in chapter 2 for polytopes, but here you have to be much more careful in dealing with the recession cones of all these polyhedra. If you want to know more, the proof is in the book. A consequence of some of the arguments used to prove the previous result is the following, that talks about, once again, now the convex hull of the union of pi as opposed to the closed convex hull. So here, if we have that the pi's are non-empty polyhedra, as in the previous theorem, but we also assume that they all have the same recession cone, then the convex hull of the union of the pi is a polyhedron, and so it coincides with the closed convex hull of the union of the polyhedra. Therefore, under this more restrictive assumption, we have that the previous extended formulation is an extended formulation for not only the closed convex hull, but also for the convex hull of the union of the pi's. Good. So now what we're going to do next is see an example of how we can use such an extended formulation for the convex hull of unions. And we're going to consider the even subsets of a set. So this set is defined as follows. So is Sn even, and is the set of all binary points that only have an even number of ones. It is possible to derive an inequality description of the convex hull of Sn even. And in fact, this is the theorem that we're not going to prove, we're only going to mention. And in fact, this doesn't use necessarily the union of polyhedra. So let's pick a ground set, capital N, with elements 1 until little n, and pick fancy S as the family of subsets of n of odd cardinality. Then we can write the convex hull of Sn even as the points in Rn that satisfy this system. So, well, of course, we have x between 0 and 1, and these inequalities are instead more interesting. What do they say? That for every subset of S, of fancy S, we have that the sum of the xi's in S minus the sum of the xi's not in S is upper bounded by the cardinality of S minus 1. It is simple to verify that all these inequalities are indeed valid for the set Sn even. In fact, well, let's pick an S in capital S, therefore cardinality of S is odd, and so the right hand side here is an even number. Now there are two cases essentially. In the first case, we have that all the xi equal to 1 are with I in S. So essentially all these guys are 0. And what about the sum? Well, since there are only an even number of xi's that are equal to 1, this sum is even and smaller than cardinality of S, so it's upper bounded by the cardinality of S minus 1. Now, in the second case, there are some xi's at 1 outside capital S. So in this sum here, so you're removing at least 1 here, so you have at least a minus 1. This is at most cardinality of S, and so you obtain this inequality. So this is again the formulation that we just wrote of the convex hull of Sn even. And the problem with this formulation is that it has exponentially many constraints. I mean, it's not necessarily a problem, but let's say that one question could be, can we obtain a formulation for this set that has only polynomially many constraints? In fact, what we're going to show is that using Ballas' union of polyhedra, we can obtain an extended formulation for this set that only has polynomially many inequalities. So how do we do that? Well, it's very natural in a sense. We define k sets S and k, and S and k contains all the binary points that have exactly k ones. At this point, we can clearly write Sn even as the union of the Sn k for every k even. So using this set n even that contains all the even numbers between 0 and n, we can write Sn even in this form as this union. Great. So at this point, we need to write down an inequality description of the convex hull of Sn k. So here it is. It's very simple. We have that this is the set of points in Rn that are between 0 and 1 and satisfy sum of the xi equal to k. So once again, it's clear that all these points in Snk satisfy this equation. What is a bit less clear at this point is that this is exactly the convex hull, and that's a very good exercise that you can work out. So at this point, we want to obtain the convex hull of Sn even as the union of the convex hull of the Snks. Great, so we can directly use a ballast result, and here it is. So we create, again, one copy of the x variable for every k in an even, and so we have that the original variable x must be the sum of all the xk's. Then for every k, we write down the system that we have just seen that describes Snk, where first we substitute the original variables with the xk copy, and secondly we multiply the right hand by lambda k, and we obtain exactly these equalities and these inequalities. Then we have that the sum of all the lambdas is equal to 1 and the lambdas are greater than or equal to 0. Now we know by Ballast's theorem that this the projection of this polytope Q onto the X space is exactly the convex hull of Sn even, and the number of variables is of course polynomial, and so is the number of inequalities. In fact, let's see. Well, the most inequalities are here because we have a bound, well, two bounds for every variable, and the number of variables is essentially n square, because we have that k is like n half, and so it's essentially n square. So this is definitely a polynomial formulation. So we have seen that the convex hull of Sn even can be written in the original space, but we need exponentially many inequalities. However, if we use Ballast's extended formulation for the union of polytopes, we obtain a polynomially sized extended formulation for the same convex hull of Sn even. The next topic that we're going to look at is mixed integer linear representability. So this topic in a sense is very different from what we've seen so far, and the proof techniques that we will use here will heavily use Ballast's union of polyhedra. Good, so what's the question? So essentially, so far in this course, we really looked at integer linear programming problems and discussed how to solve them, essentially, and a little bit on how to model them. What we want to do now is very different, because instead the question is what are the problems that can be actually written as mixed integer linear programming problems. And so what we want to obtain is essentially a characterization of all the sets that can be written as the set of feasible solutions to a mixed integer linear programming problem, possibly using additional variables. So we now give the definition that is at the heart of this section. We say that the set capital S is a mixed integer linear representable, and we're going to write in short MILR, if it is the projection of a set of points that can be written in this form with rational data. So what is this form? Well, we have a bunch of linear inequalities in a space that contains the x variables, which are the variables where the set S lives, and then we're allowed to use auxiliary variables y and z. Why do we need two types of additional variables? Well, because the y are allowed to be continuous and z are only supposed to be discrete. And our original space, we can have just continuous variables. So this is a little bit of a technical definition, but essentially you can easily convince yourself that all the sets that can be obtained as projection of mixed integer linear sets are exactly sets S of this form. So deciding if a set capital S is mixed integer linear representable is already non-trivial in dimension 1. So let's just see a few examples to just get an idea of when a set is representable or not. So in the first example, we have this set. So we can just draw it, represent it in a picture, and algebraically it's described in this way. So this is the set S1. It contains then the origin, then the segment between 2 and 3, 4 and 5, 6, 7, 8, 9, and it repeats forever in this fashion. It's easy to see that this set is mixed integer linear representable. Now, there can be several ways to write down S1 as the projection of a set as in the definition of mixed integer linear representability, and this is just one. So, of course, you might be able to come up with different ones. So let's just check, essentially, that this system works. So once again, x is our one-dimensional original variable. Then we have one additional continuous variable and one additional discrete variable. So z is also supposed to be greater than or equal to 0, so we can just look separately at all the positive integers z. So for z equal to 0, we obtain that y is exactly 0, because it's between 0 and 1, but at most 0. And so we obtain that x is 0 plus 0, so 0. So that's the origin. That's how we obtain the origin. Next, for z equal to 1, well, what happens is that we have y at most 1, which is already implied by this. So y here becomes as a segment between 0 and 1. And so x is such a segment plus 2z, which is exactly 2, because z is 1. So we obtain the segment between 2 and 3. And so on and so forth. As you can see, for larger z, we will obtain that y is always essentially the segment, and it's added to an even integer number, and that's how you obtain all the consecutive segments. Good. So let's see then another example. Here it's very similar. We have again the origin, but now instead of having several segments here that repeat, we only have one half line that goes on forever on the right. Good. So also this set is mixed integer linear representable, and we can easily at this point write down such a system that describes this set in an extended space using essentially the same idea as in the example 1, but what's the trick? That we're gonna make the segments longer. So in this case, they are long 1.5. And then we're going to repeat them every 1.5 length. So in this way, essentially, this half a line is obtained by merging together consecutive segments that touch each other and form in this way this half a line. So let's again check exactly what we obtain. We have, as before, z integral with z greater than or equal to 0. So for z equal to 0, we obtain y equal to 0 as before, so x is 0, perfect. Then for z equal to 1, we obtain y between 0 and 1.5. And so here we have the segment between 1.5 and 3. Next, for z equal to 2, we obtain the same segment, and here we obtain the segment from 3 to 4.5, and so on and so forth. So we obtain in this way all this half a line. Great. So let's see now this example, S3. And this is very similar to the first example that we've seen. If you remember, in the first example, we had the origin and then a bunch of segments that repeated evenly. Here it's kind of the opposite, because we have a segment here between 0 and 1, and then we have all integer numbers, 2, 3, 4, and so on and so forth forever. And so it's quite surprising that actually this set is not mixed integer linear representable. And at this point, you just have to believe me. So no matter how hard you try, you will never be able to come up with an extended formulation for this set. At this point, I don't have a way of convincing you that this set is not mixed integer linear representable, but we will see later on, after we give our characterization, that we can actually fully understand why it's not. Then let's see a couple of other examples of sets that are not mixed integer linear representable, which can take, in a sense, kind of a different look. So here we have the set of x that are equal to 2 to the r for r natural number. So we have 1, 2, 4, 8, 16, and so on and so forth. So you see here we just have points, we don't have any segment, but they repeat in this strange way where they're not evenly spaced. It turns out that also this set S4 is not mixed integer linear representable. Finally, as a last example, let's look at all the line R except for the open segment 0, 1. Also, this set is not mixed integer linear representable. So we're now ready to state and prove our main result on mixed integer linear representability. And this is a full characterization. So it's an if and only if. It tells us exactly when a set in Rn is mixed integer linear representable. So what's the condition? So if and only if there exists rational polytopes, P1, Pk, so finitely many polytopes, and finitely many vectors R1 until Rt, integral such that S can be written as the union of all these pi's plus the integer cone of all these rays. So let's now prove it. We have to prove an if and only if. So let's start with the direction from left to right. So we have, so our assumption is that the set is mixed integer linear representable. We want to show that it can be written in the form below. And this form, so union of polytopes plus integer cone of integral vectors, looks very similar to something we've seen not so long ago. In fact, in the proof of Mayer's theorem, we at some point considered a set which took exactly this form. So it's no surprise that we're going to use that result, which we formalized in the corollary just after Mayer's theorem. Good, so let's start. We have our set S that is mixed integer linear representable. Let's just use the definition at this point. Then S is the projection onto the X space of a set S tilde, where S tilde is of the form, so S tilde equal to the set of X, Y, Z in some polyhedron Q such that Z is integral, with Q equal to the set of points x, y, z in a polyhedron. So ax plus by plus cz less than or equal to d, and all the data is rational. A, B, C, D, rational. Okay, so now we immediately apply the corollary that we saw after Mayer's theorem to write down a different form but equivalent of S tilde. So by corollary 4.31, there exist rational polytopes Q1 until Qk, so finitely many, and integral vectors let's say S1 until St, such that S tilde is equal to the union for I that goes from 1 to k of the Qi's plus the integer cone of the SJs. So at this point, we're interested though in the set S instead of S tilde. So what we have to do is project S tilde onto the original X space. So we're going to project separately all the QIs and all the vectors in the integer cone. So defining Pi as the projection onto the X space of each QI for every I, and Rj as the projection of each Sj, we have S equal to the union for I equal 1 until k of each Pi plus the integer cone of R1 until RT. And this is exactly the form that we want because every Pi is a rational polytope because it's a projection of a rational polytope, and each Rj is also integral because it's just a projection of an integral vector. Let's write it. Great, so this concludes the proof of the direction from left to right. So let's go back to the statement for a second. So we now have to show the reverse direction. So essentially we need to pick a set S in this form and show that it is mixed integer linear representable. So essentially we need to write a mixed integer linear programming formulation for it. So let's change page maybe and prove this other direction. So for the converse, assume that S has the form union for I that goes from 1 to t of Pi's plus the integer cone of R1 until RT as in the statement. And so now I need to write the formulation, the description of every Pi. So for every I, let AIX less than or equal to BI be a rational system defining Pi. So then let's write down the formulation for the set S. So how can we do it? Let's see. We can write S as the set of X that satisfy. So let's start by writing the union of the polytopes. And this we know very well how to do it because we've done already this at the beginning of this section. So this is X equal the sum of xi, where we create a copy of the variables x for every polytope pi. So for I that goes from 1 to k. Now we write down the system of polytope I with variable xi and multiply it on the right hand by some new variable delta I, and this is for I equal 1 until k. Then we have that the sum of the delta I equal to 1, again for I equal 1 until k. And then we have delta greater than or equal to 0 and the delta in zk. Good, so this is a formulation for just the union of the PIs. Now we have to add to it the integer cone of these rays. So how are we going to do it? Well, we add it directly to the x, to the first equation here in my system. We add plus the sum for j equal 1 to t of the mu j rj, and of course we need mu greater than or equal to 0 and mu in zt. And this is exactly a formulation for the set S. So, by the way, in our formulation for polytopes that we saw back in chapter 2, we understood very in detail why it works, and there we had explicitly the box constraints, which made it clear that when delta I is equal to 0, then the only solution to this system is the origin. Here, even though we haven't written explicitly the box constraints, everything still works in the same way, because since every PI is a polytope, when you set here delta I equal to 0, you obtain exactly AIXI less than or equal to 0, which we know is the description of its recession cone, and since PI is a polytope, the recession cone contains only the origin, so xi equal to 0. So let me write it here so that you remember it. And we're done. So thus S is a mixed integer linear representable. And that's the end of our proof. So we have shown that the sets that are mixed integer linear representable are exactly those that can be written in this form: union of finitely many polytopes pi plus an integer cone of integer vectors. And note that these sets must contain all rational polyhedra. In fact, it's clear from the definition of mixed integer linear representability that a polyhedron is always mixed integer linear representable. However, you can also see it in a different way that somewhat tells you a little bit more. It follows from the proof that we have just seen that a rational polyhedron Q can always be written as just one polytope plus the integer cone of finitely many integer vectors. Before the theorem, we saw 3 examples of sets that are not mixed integer linear representable, which means, due to our theorem, that they cannot be written in this form as the union of finitely many polytopes plus integer cone of finitely many integer vectors. So let's see now, we should be able to prove that, for example, our S3 is not mixed integer linear representable. So how can we do it? Now that we have our characterization, we can indeed. So we prove it by contradiction. So let's assume that S3 can indeed be written in this form. So the first thing that we notice is that S3 is not bounded, of course, because we can have points, integer points, which are as large as we want, which means since all the union of these finitely many polytopes is bounded, it means that we must have a vector here in the integer cone that is different from 0. So let's say without loss of generality that the first R1 is different from 0. Secondly, we note that S3 contains this segment between 0 and 1, which means that at least one of the PI must be a segment. In fact, you can easily check this because if they're all not segments, they're all points, and points plus integer cone of integer vectors, you just obtain a bunch of points with no segment whatsoever. So let's say that P1 is a segment. But then look at P1 plus integer cone of R1, which of course is a subset of our set, and this will contain segments arbitrarily far from the origin, and so inevitably you will contain points not in S3, which gives a contradiction. Good, so you see that one use of the characterization theorem that we just proved is also to show that a set is not mixed integer linear representable. The next thing I want to do is observe that if a set is mixed integer linear representable, then we can also use the previous theorem to write down the convex hull of such a set. And this is exactly obtained by taking the representation that we obtained in the previous theorem and just take its standard linear relaxation. So here is the formal statement. So let S be a set that is mixed integer linear representable, which means that it can be written in this form. So as the union of finitely many rational polytopes plus the integer cone of finitely many integer vectors. And now let's say that Pi is described by the system AIX less than or equal to Bi. Then we write the polyhedron Q, which is the standard linear relaxation of the representation that we obtained in the previous theorem, which is this one described here. And we can show that the convex hull of S is exactly the projection of this polyhedron onto the X space. Let's prove this corollary. To prove this corollary, the first thing we want to do is write down the convex hull of S in a nice form that allows us to write down easily a description of conv S with the linear inequalities in an extended space. So let's do it. Let S be as in the statement. Then, so the way I want to write conv S is the following. Conv P1 union Pk plus the cone of R1 RT. And so what do we know about this set? Well, for sure it contains S, okay, because S is just a union of those PIs plus the integer cone of those vectors. And it surely contains conv S, because we're taking S and instead of convexifying it, we convexify separately the two parts in the Minkowski sum. But in fact, this really is conv S. In fact, let me write it, the last containment is an equality. Why? Well, the reason is that the set in the middle is in fact a polyhedron. And since conv S is the smallest convex set containing S, if it contains a convex set containing S, then it must coincide with it. Let's write, in fact, the set in the middle Great. So now the rest of the proof proceeds somewhat similarly to the second part of the previous theorem we've proven. So essentially, we use Ballas' theorem to write down a description of such conv of P1 union Pk, which we know very well how to do due to Ballas, and then on top of that, we add at the end the cone. So let's start. Since P1 until Pk are polytopes, a description of the convex hull of the union is given by Ballas theorem. So it was, now we know this by heart, x is the sum for I equal 1 to k of the xi's, where ai xi less than or equal than delta I bi for I equal 1 until k. Then we have that the sum of delta I equal to 1 and delta greater than or equal to 0. So this just gives me the description of the convex hull of the union as we have written. Now we have to add back the cone of R1 RT, and we do it very similarly to what we've done before in the previous proof. So let me write it down here because I want to edit then this formulation. In order to obtain a formulation for conv S, we have to take into account the rays R1 until RT. So how do we do it? We add to the x here plus the sum for j equal to 1 until t of the mu j's, rj's, and then we have mu greater than or equal to 0. And this is exactly the formulation in the statement, and so this concludes our proof. And this also concludes this section about the union of polyhedra.